FRQ question number 1. This is a calculator-related problem. Let f be an increasing function defined by x values greater than or equal to 0. The table gives the values for f of x at the selected values of x, and the function g is given by the following equation. Let h be defined by the following. Find the value of h of 5 as a decimal approximation. As a reminder, we're going to round to the nearest thousands, or 3 places to the right of the decimal, or indicate if it's not defined. This is the key. Show the work that leads up to your answer. So we can use a calculator as a tool, but we do need to show our work. So I'm going to use the booklet as practice, where you'll be showing your answer. As a reminder, you will see the questions on the screen, but your answers are going to go for FRQs, are going to go into your test booklet. So let's get started. All right, so we know that h of 5 is equivalent to g of f of x. And again, we're inputting 5 for our input x value. And so I am going to show all my work here. So what is f of 5? So I look back up to the table. When the input value, or x value, is 5, the output value for function f is 34. Now I believe, because it said show the work that leads up to your answer, I believe that taking the extra step to show all of your work is important. Now I'm going to go to function g of x, and wherever I see an x, I'm going to input in 34. Okay, let's use the calculator, and I'm going to start by inputting this into the top. So I have 34 raised to the third minus 14 times 34, subtract 27. I see a lot of times where students make a mistake and then go divided by 34 plus 2, and they forget to use parentheses. So I'm going to suggest that you are going to calculate the numerator and calculate the denominator and then divide them. We don't want to make a simple mistake. So h of 5 is equivalent to, and we're going to round, so I'm going to make this approximately 1077.806. So I'm looking to the third number to the right of the decimal, and then because the number behind it is a 5, I'm going to round up. Let's look at part B. Find the value of the inverse of f, or indicate that if it's not defined. Okay, we can do that next. Give me 1 second. I'm going to flip over here. So I'm going to write in part 2 of A at this portion. Well, let's examine f of x. So first we have to decide, does the function have an inverse? So the function does have an inverse because it's 1 to 1. What does that mean? It means every x value corresponds to exactly one y value. So every x value corresponds to exactly one y value, and every output, or y value, corresponds to exactly one x value. That's how it's defined, as 1 to 1. So we're going to write down all the given information here. We want to be as detailed as possible. This is what we know about the function f of x. So we're going to say f of x is increasing. Now we have to say where the function is increasing. F is increasing, defined for x values greater than or equal to 0. Now we need to let them know that there is an inverse. So the inverse of f does exist, since the function f of x is 1 to 1. Now, what does it mean to be 1 to 1? This means each, and you can use the word inputs or outputs or x's or y's. I'll keep it the same, so I'll keep x and y's. This means each x value corresponds to exactly one y value, and each y value corresponds to exactly one x value. So we've stated this is the reasoning why we know that there is an inverse, and now we can actually say for the inverse function, when the input value is 4, what is the output value? So let me go back up here and just review for us that in this original function, when the input value is 1, the output value is negative 10. And when the input value is 2, output's negative 5, input value is 4, or 3, the output value is 4, blah, 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 right? This is for the function f of x. Now for the inverse function, we're going to take and we're going to flip the input and output, or flip the x and y. And by doing so, then we can see that when the input value for the inverse function is 4, the output value is 3. As a reminder, we are not going to circle anything. If you circle it, that's the only thing that can be graded. So a lot of students may make the mistake of circling. Nothing is going to be circled. If we make a mistake, we can cross it out. We don't have to take time to erase it all. Part B says find all values of x and decimal approximation. Remember, we're going to round to the nearest thousandths, for which g of x equals 3, or indicate if no such value exists. Okay, so what we're going to do is we are going to find out where does this function equal 3. So I'm going to use 3 equals this function, and I'm going to graph and find the intersection. So I'm going to first reset my calculator, go up to y equals 3, and then let's plug this in. Now let's take our time to use parentheses in the numerator and parentheses in the denominator. So I have x to the third, subtract 14x, subtract 27. Again, you're going to hug with parentheses the numerator and the denominator. We likely will need to expand this. Let's do zoom fit. And we can see exactly here where it does intersect. So second trace intersect. Okay, so the x value shows where they intersect. All right, so I would go ahead and write, using a graphing calculator, I found the intersection of, and maybe, you know what, maybe we want to redefine this. This is going to be, we have g of x equals, what did it say? G of x equals 3. Let's just do this, of y equals 3, and y equals this. Using the graphing calculator, I found the intersection of the two functions above. And I'm thinking more about this. I think I want to keep this in the exact notation they provided to us. So let's keep this as g of x equals this quantity, and g of x equals 3. Okay. Using a graphic calculator, I found the intersection of the two functions above, and so we can say, it says indicate the values of x and whiches, and so this is going to be x is approximately 4.875. All right, determine the end behavior of g of x as x decreases without bound. Okay, that means as x goes to the left without bound. So how do I correctly write this? The limit as x goes to negative infinity of g of x. And so this is either going to be going up, going down, or staying constant at some value. I'm going to come over here, I'm going to take out the 3, and we're going to look just at this function. Okay, so as I go to the left without bound, we can see that this function is going upwards. It has no limit how high it goes, so it's up to positive infinity. Let's look now at part C. Based on the table, which of the following function types best models the function linear, quadratic, exponential? Students who took this test in May of 2004 were able to actually have a paper copy of the questions. Unfortunately, now it has changed, so you will see the questions on your computer, and then you'll be given this booklet in order to write your answers. So I am going to demonstrate how I get the answer in this portion, and maybe actually I should have put this right here, but here I've got to do the work. So let's see here. How do I go from negative 10 to negative 5? I am adding 5. Now negative 5 to 4, I'm adding 9. 4 here, I'm adding 13, and I'm adding 17. Well, I know that means it's not linear. I am not multiplying or dividing by a number. It's not exponential here. Let's check the second difference. Here I'm adding 4, here I'm adding 4, and here I'm adding 4. That tells me it's going to be quadratic. That's the model. Now, why did I choose quadratic? What is the reasoning? And that's because the second difference is the same. I chose a quadratic model because the second difference is the same. And maybe I would rewrite that here, assuming that they want to see the work here. What is your reasoning? We can see the values. They want the reason for the values. So maybe we could draw an arrow back up here so they could see our work.